This presentation highlights Giorgio Parisi and the 2021 Nobel Prize in Physics, awarded for revealing how disorder and fluctuations can cooperate to create predictable behavior across scales. Parisi's work shows that apparent randomness in materials and systems can hide underlying patterns, and the Royal Swedish Academy recognized this insight as pivotal from atomic to planetary levels. Giorgio Parisi's scientific journey moved from early work in quantum chromodynamics to pioneering breakthroughs in spin glasses, then to multifractal studies of turbulence under ERC funding, and finally to a solo Nobel Prize for complex systems. Each step built new theoretical tools that connected microscopic disorder with large-scale emergent behavior, forming a coherent career-long theme. The key discovery is that disorder and fluctuations don't just muddle systems, they can cooperate to produce collective, predictive power. The slides show a flow from atomic structures through complex materials to planetary phenomena, illustrating how seemingly chaotic components can synchronize and yield models that capture large-scale behavior despite microscopic randomness. The 2021 Nobel Prize was split to reflect two complementary achievements. Half recognized climate modeling advances by Manabey and Hasselmann, while the other half honored Parisi's deep theoretical contributions to complex systems. This distribution underscores how empirical climate predictions and abstract statistical physics together strengthen our understanding of Earth and other complex phenomena. Parisi's 1,979 80 discoveries introduced replica symmetry breaking and the Sherrington-Kirkpatrick solution, revealing an ultrametric hierarchical organization of many pure states. The fractal free energy landscape metaphor captures how systems settle into many local minima, explaining slow dynamics and memory effects in disordered materials and providing a new conceptual language for complexity. The Parisi solution has become a versatile toolkit bridging disciplines. It helps explain learning dynamics and generalization in neural networks, sets limits for error-correcting codes, guides combinatorial optimization to near-optimal solutions, and maps machine learning loss surfaces to complex energy landscapes, transforming abstract physics concepts into practical frameworks across fields. Stochastic resonance describes how weak Milankovitch orbital forcing, coupled with internal climate noise, can trigger quasi-periodic glacial-interglacial transitions. The ball-in-a-well illustration makes this intuitive. Tiny periodic nudges, plus random fluctuations, can push the climate system between states, offering a plausible mechanism for long-term climate cycles without requiring large deterministic forces. Parisi showed how random fluctuations can synchronize with tiny periodic signals to produce emergent order and amplification. This principle has been verified in laser dynamics, neural rhythms, and signal processing, and it reshapes our view of natural variability by demonstrating that noise can enhance, rather than obscure, subtle patterns across many systems. Looking more deeply at turbulence, Parisi and collaborators explained how energy cascades concentrate into filaments and produce anomalous scaling beyond Kolmogorov's 1941 theory. The multifractal perspective accounts for intermittency and unusual exponents by recognizing that energy transfers are uneven and concentrated, which resolves long-standing discrepancies between theory and observed turbulent behavior. The multifractal formalism provides a unified way to quantify complexity across scales, from rain and precipitation models to solar wind plasma, from financial market volatility to heartbeat variability. By treating disorder and fluctuations as scale-invariant features, this approach uncovers common patterns and helps build models that apply across very different natural and socio-economic systems. Statistical physics becomes a universal toolkit when its ideas about disorder and energy landscapes are applied to modern problems, guiding AI generalization through energy landscapes, informing protein folding algorithms, analyzing ecosystem resilience and tipping points, and improving pandemic models for disordered populations. In each case, the same basic concepts help predict and control complex behavior. Current ERC projects on glassy jamming and quantum optimization aim to uncover deep links for next-generation innovation, exploring complex disordered systems and computational efficiency in quantum setups. The work seeks a unified conceptual framework of information, geometry, and matter, with future impact expected in advanced materials and algorithms for challenging optimization problems.